Oh, right. Let's look at this. We're going to do some comparison tests to determine whether a series converges or diverges. So we got to determine if an unknown series converges if it looks similar to a known series. This one looks a lot like my geometric series friend from n equals 1 to infinity, 1 over 2 to the n, or 1/2 to the n. And I know that 1/2 to the n converges because it's a geometric series where the thing I'm multiplying by, also known as the common ratio, is less than 1. So I know that that geometric series converges. To determine if this one converges, here's what I'm going to think. I'm going to think graphically. If I did 1 over 2 to the n, 1/2 to the n, that will look like this. If I do 1 over 2 to the n plus 1, again, I'm pretending this is 1 over 2 to the x plus 1 and 2 to the x, because I'm not doing distinct points, we would be less than that whole time. So if I know that this one converges, and this one's always less, then this one has to converge. So converge. So I'm comparing the one I'm given to one I already know. And since this one is less than a convergent series, then that series will converge. Let's check out this next one. So this next one looks like 1 over n, which is called the harmonic series. We've already established that 1 over n diverges. If I again think graphically, if I have 1 over n, it looks like this. Natural log of n over n will be bigger, right? Well, if this one diverges, and this one's always bigger, then that one also has to diverge. So I compared it to a known divergent series. And if my unknown series is always bigger than a series we know diverges, then my unknown series also has to diverge. Now, I could consider the same idea on the next one. So compare this one to, I'm going to go with 1 over n squared. Because do you agree that this is a fraction, and I'm adding more to the bottom, and therefore the bottom will be smaller, so this one will be smaller than this one. We know that this one converges, so that means this one has to converge. So one has to converge. So I'm going to compare it to 1 over n squared. Now, this last one I have an issue. I have many issues, but I have an issue with this one. Because I was adding to the fraction, that made that number smaller. Here I'm subtracting. So if I consider this one, I'll make this one yellow, it's going to be a little bigger than the blue. I know the blue converges, I know the purple converges, therefore. I don't know if the yellow converges. So I can't use this same idea. Now, some people will call this the direct comparison test that I'm talking about. So the direct comparison test says, if I have a known convergent series and I have an unknown series that's always less than that, then the unknown has to also converge. Similarly, if I have a known divergent series and I have an unknown series that's always more than that divergent series, could be equal to, then the unknown series will diverge. Obviously, I'm thinking above the kind of axis, above the x-axis. All right, what do we think is going to happen? I feel like, so I want this to converge. I want to converge because I want it to behave just like this. The -1 is not going to change really how quickly this thing goes to 0. So I think I can claim this is going to converge. But that's kind of more an argument of like when n gets really, really big. So my argument is when n gets really, really big, these will behave the same. So by n gets really, really big, let's go ahead and go to infinity. And let's compare the thing I don't know to the thing I do know to the thing I don't know. All right, let's do some algebra. So let's flippy flop. So that's going to be 2 to the n minus 1 over 2 to the n. Basically, I'm going to multiply top and bottom by the 2 to the n minus 1. They will cancel here. And now, let's get fancy mathematically. Ooh, actually, here's what I want to do. I want to throw in l'hôpitals, because we haven't talked about it recently, so I want to throw it in. The limit as n goes to infinity of 2 to the n minus 1 equals, goes to infinity. I don't know if I want to say equals. Makes me uncomfortable to say equals. It goes to infinity. The limit as n goes to infinity of 2 to the n goes to infinity. So now I can use l'hôpital. And I can take the derivative of the top and the bottom. Well, if you can't remember the derivative of 2 to the n, think of it as 2 to the x. So y equals 2 to the x. Take the natural log of both sides. Take the derivative. So the derivative of natural log of y is 1 over y dy dx. Natural log is a derivative you have to know. The derivative of natural log of, that's an x natural log of 2 there. The derivative of x natural log of 2 is natural log of 2. Multiplied by y, but y is also known as 2 to the x. Oh, so that's the derivative. So that means that this limit is equal to the limit as n goes to infinity of 2 to the n ln 2 over 2 to the n ln 2. Oh, that's 1. Okay, so as n gets huge, we get 1 for the limit. So these things behave the same. And so my claim is, if I can use a limit, if I can do the limit as n goes to infinity, and these things, we get a number, then these series will behave the same. This was convergent, but I think the same argument will occur with divergent series. Oh, look, the limit comparison test. So we have AK and BK are two series. If we get a number then they do the same thing. If we get 0, okay, that's kind of a particular case. And if we get infinity, kind of a particular case. Because this one's saying, if I know that BK converges and it totally dominates AK, which is why the limit is 0, then AK also has to converge. In this one saying, if I know BK diverges, and it totally dominates AK, so that's why we get infinity, then AK will diverge also. So two particulars there. The most important step is right up there with the first one.